So let's do a quick review of acid and base solution chemistry. One of the reactions that we were asked to know, recognize, was the following. When we have an acid reacting with some sort of base, what? I'm in the middle of a recording. So acids reacting with a base to usually produce some sort of salt, MgCl2, aqueous, plus water. So this was a standard acid-base neutralization reaction. Well, it turns out that this is one of the reactions we actually do in the lab. We have a special device called a burette, which we fill with a solution, and we have our base of unknown concentration at the bottom. So we have a 10 milliliter sample of MgOH2 of some unknown concentration. We don't know what it is. And we have a burette that we have loaded with a 0.050 molar HCl solution. And we dropwise add the HCl to the base. And this is a process called titration. We know that this starts at, if we had 15 milliliters at the start and we were to slowly add it until there was 22.5 milliliters total, we could figure out that 7.5 milliliters of HCl were added. So once we know that, we have now added 7.5 milliliters of a 0.5 molar HCl solution. And then we can use that to figure out the number of moles of magnesium hydroxide that were in that reaction. In many acid-base reactions, we often have to do one chemical reaction before we actually do the analysis. Again, the reaction before the reaction. This is a perfect example. In acid-base equilibrium, we often have a neutralization that takes place, and then we care about what happens after the neutralization. Neutralization was last semester. And now we're going to figure out what happens after neutralization. So in this case, we know how many milliliters of HCl we have, what the molarity of the HCl is, and so we know that we have a 7.5 milliliter HCl solution. We know that for every 1,000 milliliters of HCl, that is equivalent to a 0.0500 moles of HCl. And from our stoichiometry, we know that 2 moles of HCl consume 1 mole of MgOH2. It says that in that solution there are 1.875 times 10 to the negative 4th moles of magnesium hydroxide. Now, if we were asking what the molarity is, we would know that that would be 1.875 times 10 to the minus 4th moles magnesium hydroxide in 10 milliliters, or 0.010 liters. That would give us a molarity of 1.87 times 10 to the minus 2 molar. Again, a molarity and a volume together tell us the number of moles. This is just like from last semester. And once we have that number of moles, we can then use stoichiometry. We can use it to predict. We can use it to predict how much was left over. We can use it to predict how much was used. Right? So these will be limiting reagent problems, these will be solution problems, and so that's where we're going to be living. I've noticed that I always say "so" at the beginning of these things. So we've spent the start of the lecture talking about what acids are, our definition of acids, bronzic acid and the Arrhenius acid. We'll mention Lewis acids later in the talk, but we're going to talk about acids usually are things that influence the amount of H3O plus in solution, because they're all tied to the equilibrium of water, 2H2O associated with H3O plus OH minus, and KW being associated with this. Acids are things that have a tendency to generate excess H3O plus. Bases have a tendency to generate excess OH minus, though another definition of that is those things that are able to accept protons. Right. So things that we normally think of as acids and bases have a tendency to affect either of these values. Now, we then talked about ways of measuring H3O plus, and we came to the realization that the amount of H3O plus, the amount of OH minus, and alternate ways of representing these, particularly pH and POH, are all tied together. So being able, given any one of these, you should be able to calculate all of the other ones relatively quickly. Here's the way it works. You're given in a problem the pH, and then you use that information. The pH is code for the amount of H3O plus, and so you have to be able to rapidly convert that into H3O plus and then use the H3O plus. Now, we talked about acids, and one of the things that we have to deal with when we deal with acids and bases deals with their strength. Are they strong acids? Strong or weak acids? And this idea of strong and weak has nothing to do with concentration. We can also talk about electrolytes in the same fashion. So strong and weak materials, strong and weak electrolytes. A strong acid, strong electrolyte, completely dissociates. What do I mean by this? If you take HCl and you plop it down into water, you get out H3O plus and Cl minus. Every single one of these HCl molecules has been converted into H3O plus and Cl minus. What that means is if you create a 1 molar HCl solution, you can be pretty sure that it consists of 1 molar aqueous H3O plus and 1 molar aqueous Cl minus. So that's our definition of a strong acid, a strong electrolyte. A strong electrolyte, like something like NaCl, again, we dissolve that into water and you'd get out Na plus aqueous and Cl minus aqueous. And we've discussed things like non-electrolytes, those materials that are covalently bound that will dissolve in water. A 1 molar sugar solution releases a 1 molar aqueous solution of sugar, regardless of formula. It doesn't dissociate any further. For us, what we care about are acids in relationship to this strong and weak behavior. And so while strong acids completely dissociate, weak acids do not. What that means is that we have some generic weak acid, which we'll just say HA, in aqueous solution that dissociates to make a little bit of H plus A minus. It turns out that this is an equilibrium, hence this weeks and weeks of equilibrium discussion, that when this dissolves, rather than completely producing H plus and A minus, thinking of it as a single arrow, we have to think of this as an equilibrium. That means that there is an equilibrium constant associated with this, which we define as Ka. Now, a more correct way to write this is that the weak acid in the presence of water interacts to form H3O plus A minus with an associated Ka. So the correct form of the equilibrium constant Ka would be equal to H3O plus times A minus, all divided by HA aqueous, the undissociated acid. Now, what this means is that we can't know what the H3O plus concentration is or the A minus concentration is directly. If we started with nothing but the acid, if we started with nothing but HA, we can write out the algebra for this. If we started with HA, we could write out the algebra for this, and we say, okay, well, let's just pretend that the starting concentration, the total weak acid, which we'll just say HAT for total, minus whatever has been consumed, the water we don't care about, will result in a small amount of the material formed. And then we can plug these values back into the equilibrium constant, get the following. Ka would be equal to, because H3O plus is the same, plus X weak acid minus X. Now you can run through the math and you'll see that this is a square term, and we can do the quadratic and solve it. But here's the important bit. All right? These are weak acids. Weak acids. What do we know about weak acids? They don't dissociate completely. So we can use our chemical intuition and say, well, they don't dissociate completely. Almost all of the acid remains undissociated. Typical weak acids, only about 1% to 5% dissociation. They don't fall apart in water. We can use this fact that they don't fall apart to tell us something. And that thing that it tells us is that we can assume that X is going to be small. One of the simplifying assumptions. If X is small, then this will be approximately equal to the starting concentration that we dealt with. If that's the case, we can plug this back into the equation and get the following. Ka is equal to X squared divided by HAT, which allows us to rearrange and solve which allows us to get the H3O plus concentration